Hi everyone, I am Santhi from Department of Mathematics and Statistics, Bhavan Vivekananda College. I am here with my lesson 16 from linear algebra on vector spaces. In this lesson, I am going to explain few theorems on linearly independent sets, basis and dimension. Our first theorem is if a vector space V has a basis B is equal to set containing B1, B2 and so on Bn, then any set in V containing more than n vectors, that is n elements, is linearly dependent. Earlier we had some results that we were discussing in Rn. All we discussed about Rn. If you have Rn, in Rn, what is the dimension of Rn? Its basis will have n elements, its dimension is n. If there is any set S with more than n vectors, then it is LD. This we discussed about Rn. Now this theorem we are going to generalize it for any vector space V. Need not be for Rn. Let us look at it. So a proof. So we are taking let V be a vector space and with a basis B is equal to set containing B1, B2, B3 and so on Bn. So in the basis of V you have n number of elements. Now what do we have to prove in this theorem is any set with more than n elements is linearly dependent. So for that we are taking a set, consider a set S. So with how many vectors? U1, U2, U3 and so on UP. P number of vectors where P is greater than n in V. So in V we have taken a set S with P number of vectors where P is greater than n. What is n? Number of vectors in basis of V. So now we have taken another set with P number of vectors and this P is greater than n. Now you have to prove that this S should be linearly dependent. Now we use here coordinate vectors concept. Whenever there is a set with some vectors in the vector space V, correspondingly there will be coordinate vectors for that for those vectors in the set. So implies there exists the coordinate vectors, coordinate vector of u1 with respect to basis B. Similarly, coordinate vector of u2 with respect to basis B. And so on, coordinate vector of up with respect to basis B. Where will the coordinate vectors be in Rn? Whatever the vector space V may be, for the vectors in that vector space with respect to given basis, the corresponding coordinate vectors will be there in Rn for some n belong to n. It depends. For some vector space, the coordinate vectors will be in R2. For some vector space, the coordinate vectors will be in R3. Depends upon the vector space. So this even in the last lesson, I discussed about these points. Now, we have to prove that S is LD. Now, let us suppose that S is Li. The set S is Li. Then, if the set S is Li, then for P greater than N, what will be these vectors? The coordinate vectors. The corresponding coordinate vectors also will be Li in Rn. This point also we discussed earlier. If you have some number of linearly independent vectors, then the corresponding coordinate vectors also will be linearly independent. Where in Rn. So now what did we get in Rn? You have P number of vectors which are linearly independent, but what did we know in Rn? In Rn, more than n vectors are linearly dependent. So here you got here for P greater than n, these are Li, but in Rn, any set with more than n vectors cannot be Li. So you are getting a contradiction. You are supposing that it is Li, but again you are saying in Rn more than n vectors cannot be linearly independent. So you are getting contradiction. Why are you getting contradiction? Because you suppose that this set S to be linearly independent. So what must be correct? S must be linearly dependent. So not only in Rn, in any vector space V which has a basis with n number of elements, then according to this theorem, any set with having more than n number of vectors must be linearly dependent. Let us come for the next theorem. If a vector space V has a basis of n vectors, then every basis of V must contain exactly n vectors. So the same type of concept, same type of point earlier I gave you when we were discussing about the main vector spaces of the type Rn or like Pn. For that, for example, suppose let us consider R2. What is its standard basis? 1, 0, 0, 1. We all know it. And what is the dimension of this? Dimension R2 is 2. We all know. Now any basis, suppose I take one more basis for this, 1, 2, and let me take minus 1, 3. This is also a basis for R2, then this will also have same 2 number of vectors. And this I discussed it when I was giving you the points about the linearly independent sets, basis of Rn. Every basis of Rn will have same number of vectors. For any, in fact, that we discussed for the type of Rn. Now the same thing we are generalizing for any vector space V, not only for Rn. So not only for Rn, for any vector space V, if a basis is having n number of vectors, then all other bases also must have the same number of vectors. Now let us try to prove this. So let V be a vector space with a basis with n elements. Now let me take, it has a basis with n vectors, it is given. So let B1 be a basis of V with n vectors, right? So what do we have to prove? Any other basis also will have the same number of vectors. So let me take one more basis. If possible, let B2 be another basis of V with m vectors. I have to prove that it will also have same number of vectors. To prove that, I am taking contradiction. Suppose there is another basis with m number of vectors. So these n and m are different. Then what do we have to prove now? These both m is equal to n. Right. So you have to prove in any any place, if you have to prove two numbers are equal, if you have to prove A is equal to B, then you have to prove that A is not less than B and A is not greater than B. If A is not less than B and A is not greater than B, then what is possible? A is equal to B. This is what we have to do at any time if we want to prove that two values are equal. So now we have to prove that m is equal to n. Now what do? I have two sets. One is B1, two bases. One is B1 and another one is B2. Basically, these B1 and B2 are also linearly independent sets in V. See, they are bases like this. You have V and this is B1, maybe they may be having same common elements or whatever it is. B1, this is B2. Now these two are bases. This is a basis and this is also a basis, but before that even these two are sets in this V. So what do is I will consider B1 as basis in the first case, B1 as basis and B2 as any linearly independent set. This is just because every basis is linearly independent. So in the first case, I will consider this as a basis and the second one as linearly independent set. Now, what did we prove in the previous theorem? Every linearly independent set, if a basis is having n number of vectors, every linearly independent set cannot have more than n vectors. Then by a known theorem, this B2 cannot have more than n vectors because B1 has n number of vectors. If B2 must be Li, then B2 cannot have more than n vectors. That means how many vectors B2 is having? M vectors. This M cannot be more than n. So what should it be? M should be less than or equal to n. This is the first argument what we have done by taking B1 as basis and B2 as any Li set. On the other hand, now I will consider B2 as a basis and B1 as any Li set. So we are changing the rules. B2 as a basis and B1 as any Li set. Now B2 has how many vectors? M number of vectors. and Li set has how many vectors? N number of vectors. Then by the same theorem, this B1 cannot have more than the vectors in B2. That is, B1 cannot have more than m vectors. That implies now n must be less than or equal to m. So in 1 you have m is less than or equal to n, and in 2 you have n is less than or equal to m. Then from 1 and 2 m must be equal to n. What do you mean by that? If you take one basis with n vectors, then all the other bases also should have the same number of vectors. Here is the third theorem. This is regarding a subspace of a finite dimensional vector space and its dimension. Let H be a subspace of a finite dimensional vector space V. Prove that any Li set in H can be expanded if necessary to a basis of H. Also prove that H is finite dimensional and dimension H is less than or equal to dimension V. So in this theorem, you have a vector space V and its subspace H. This is H. This is what given. Then any Li set in H, suppose I take a set S. This is Li set. In H can be expanded if necessary to a basis of H. So if this Li is there, you can make any linearly independent set as a basis for H. When will Li set be a basis? If it also spans, then it will be a basis. Right. So if it cannot be spanning, then you can extend it. That means extending means adding more elements to that. You can obtain a basis to H. That is what you have to prove. And the second point you have to prove is prove that H is also finite dimensional. The subspace is also finite dimensional. When V is finite dimensional, H is also finite dimensional, and dimension of H must be less than or equal to dimension of V. These are the points we are going to discuss, prove in this theorem. Let us start proving the theorem. So there is a subspace H. So first let us suppose that if H is equal to set containing 0, that means it's only having 0 vector. Then what happens? Then what will be dimension H? 0. So then obviously the dimension 0 will be less than or equal to dimension V, whatever the vector space. So our this theorem will be completed if H is having only 0 vector. You don't need to prove anything. So let us take let H is not equal to set containing 0. What do you mean by H is not equal to set containing 0? It means that even H has some other non-zero vectors. It is like this. If H is equal to 0 means it has only one vector. If H is not equal to 0 means H may have like 0, A minimum, where this A is non-zero. Or it may have one more element which is non-zero. That means not only 0 element, it will have some other non-zero elements also. That's what we mean by H is not equal to set containing 0. So now I have taken H not equal to set containing 0. Now I'll take a set, a linearly independent set in H. That is what our task here. Take a linearly independent set in H. Then you have to prove that it can be extended to form basis. So I am taking a set S with how many vectors? K number of vectors. Be any linearly independent set in H. Right. Now where is S here? S is in, this is H and this is V and this is S. Now S is a subset of H means even S is a subset of V. That is what I have written here. S is a subset of V. And how many vectors S is having? K number of vectors. And K number of vectors compulsory, it will be less than or equal to dimension V, because V is, this S is subset of V means it has K vectors, means number of vectors in S must be less than or equal to number of vectors in V. So this K should be less than or equal to dimension V. Okay, fine. Now let us look at how can we prove that this linearly independent set S will can be added or can form a basis either S or by extending. Now, if since S is Li, if S spans H, then it forms a basis, because we know basis is a set which is Li and which also spans. Already it is given Li. If it also spans, then it forms a basis for H. If this is the basis for H, then what will be dimension of H? Will be K, because number of vectors in basis. So dimension H is equal to K, which is less than or equal to dimension V. Right. So this theorem is proved when S itself forms a basis. Suppose if S cannot be basis, means if S does not span H. We suppose S spans H. Suppose if it is not true, S does not span H. What do you mean by S does not span H? We mean by S does not span H, that means all the vectors in H cannot be spanned by S. That means there should exist at least one vector in H which is not a linear combination of elements of S. So that's what there exists a vector in V. That vector I am taking it as UK plus 1, which is not a linear combination of U1, U2, U3 and so on UK. Is it clear? If all the vectors in H are linear combinations of S, elements of S, then S will span H. But we have given here that if S does not span H, that means there will be some element in H which is not a linear combination of elements of S. That element I am taking it as UK plus 1. So what is UK plus 1? It is not a linear combination of these K vectors. Now I am taking a new set S1. So what are the elements in S1? U1, U2, U3 and so on UK. But up to here the elements of S. Adding UK plus 1. That is an extended set of S. I added an element. Now in S1, what is the element I added? An element UK plus 1 which is not a linear combination of these, which is free from all these. Then S1 still remains Li. Why? Because you have added an element which is not at all a combination of other vectors, free from other vectors. So up to UK already they are linearly independent, and you are adding one more vector which is not at all a linear combination of these. So S1 still remains Li. Then if S1 spans H, whatever S1 you got now, if that is spanning H, then it forms a basis for H. And what will be dimension H then? K plus 1, number of vectors in basis. Then that is less than or equal to dimension V. Our theorem will be proved. Otherwise, that means if S1 does not span H, then again the same argument. If it is not spanning H, means there should be some element in H which is not a linear combination of elements of S1. That's what we write here. There exists a vector in V, let it be UK plus 2, which is not a linear combination of U1, U2, U3 and so on UK plus 1. So there is one more element in H which cannot be a linear combination of these vectors. Now we are forming a new set S2 is equal to U1, U2, U3 and so on UK plus 1 and adding UK plus 2. Then still S2 is Li, because you are adding a vector UK plus 2 which is not at all a combination of the previous vectors. So still that set S2 will be linearly independent, and this is an extended set of S still. Now we continue the same above process of extending S till it spans H. So you will go on add the vectors to S which are not combinations of previous vectors. Then since how long you will do that? Since the number of vectors in Li set cannot exceed the dimension of V. So suppose dimension of V I have like this, dimension of V is equal to 10, and I have S with 5 vectors like A1, A2, A3, A4, A5. These are Li. Then I will add one vector A6. S1 will have all up to A6. If this spans, then this is a basis. Otherwise, I will add one more vector, A1 up to A6, A7. Then how long I can add? I can add A8, I can add A9, I can add A10. Then what happens? 10 vectors already if you get. If you add one more vector, you cannot add. Then it will not be Li. Why? Because the dimension V is 10. More than 10 vectors will be linearly dependent. So a maximum at this step you will stop. You have to get basis for the vector space V. That is what our argument. So the number of vectors in a Li set cannot exceed the dimension of V. After a finite number of steps, we must obtain an extended Li set of S which also spans H. So after adding those many vectors, which is a difference between dimension V and the number of vectors in S, you must get a Li set which also spans. Hence, we can obtain a basis for H. Then what will be the dimension, and dimension H must be less than or equal to dimension V, because you cannot add more than the dimension of V. That set S cannot have number of vectors which is more than the dimension of the vector space V. So at the maximum you will get sometime at dimension H should be less than or equal to V. Now here is the another theorem, that is basis theorem. What is its statement? Let V be a p-dimensional vector space, that is p greater than or equal to 1 with more than one dimension, more than or equal to one dimension. Then there are 2 points. Any Li set exactly p elements in V is automatically a basis of V. Second one, any set of exactly p elements that spans V is automatically a basis of V. Now this same point we discussed earlier for Rn. If you have the vector space Rn and if you have Li set with n vectors, then it is a basis. Or if you have a set with n vectors and it spans Rn, then it forms a basis. So if the dimension is n, Rn dimension is n, Li set with n vectors can be a basis, or if a set spanning set which has with n vectors, right, it will be also a basis. Any one is enough. Now the same thing we are proving in general for any vector space V. So again let us look at the statement. If V be a p-dimensional vector space, the dimension of V is equal to p, then any Li set with exactly p elements automatically a basis of V. In the same way, any set of exactly p elements that spans V is automatically a basis of V. Let us prove this. Let V be a vector space and the dimension V is equal to p, that is p greater than or equal to 1. Now it comes first point. Let S be any Li set in V with exactly p elements. Then by a known theorem, S can be extended to form a basis for V. That is what we have proved the previous one. But that means S will be having more than p elements. But every basis of V must contain exactly p elements. That also we proved it. So you are getting these two. S can be extended and every basis must have exactly p elements. What do you mean by that? S itself must be a basis for V. There is no chance to extend S. If you extend it, it will have more elements, then it cannot be a basis. But according to a theorem, every Li set can be extended. Then what is the common point for both? S itself must be a basis for V. Now the second point, let S be a set with exactly p elements and that span V. So this S is spanning V now, and how many elements it is having? P elements. Then by spanning set theorem, there must exist a subset of S that forms a basis for V. So what is that spanning set theorem? If you have a spanning set, you can delete vectors from that and you can make a basis. Deleting vector means getting subsets. In that case, what happens if S is, if you take subset of S, it will have less number of vectors. Then what happens? You will get a basis with less than P number of vectors. But every basis of P must contain exactly P elements. But you are getting a basis with less than P vectors. These two are contradictions. Then what is possible? Only S itself forms a basis for V. That is the only possibility. Hence the theorem is proved.